In this video, we're going to talk about series, in particular infinite series. There's just an infinite sum of numbers. So here's a simple series. This is called the harmonic series. It's the reciprocals of the positive integers added together. And you have one, a half, a third, a fourth, and so on forever. In summation notation, we can write this like that. Remember this capital sigma, it's a Greek letter. Capital sigma stands for sum, and you're going to add up 1 over n as n starts at 1 and goes all the way up to infinity. You can think of the decimal expansion of a number as a series. So for example, 1/9, which is 0.1 repeating. So that's a tenth, and then 100th and 1,000th and so on. Those are powers of 10. That's how our base 10 decimal system works. And so 0.1 repeating is 1 over 10 to the nth power as n goes from 1 to infinity. So 1/9 is equal to the sum of this infinite series. Now what is this doing here? So, strange. Not sure why. Which one is that making that happen? Oh, okay. So, infinite series might add up to a finite number. And you can see in this case. So we call this series here convergent because it adds up to a number. Some series don't add up to some finite number, and those series are called divergent. And we'll talk about what exactly I mean by those a little bit later. Now, one of the easiest ways to why is this not showing up? Okay. One of the easiest ways to get a divergent series is if the terms don't approach 0. So if we're adding up some sequence a sub n as n goes from 1 to infinity, if these terms aren't getting smaller, closer to 0, then this can't possibly add up to be a finite sum. It has to diverge. If the limit does equal 0, that does not guarantee that this thing converges. So the terms that you're adding up might get smaller and smaller and smaller, closer and closer to 0, but it still might add up to infinity. And one example of that is the harmonic series. The limit as n goes to infinity of 1 over n is indeed 0, but the harmonic series, which is the sum of those reciprocals, does diverge. It was proved a long time ago, at least as far back as the 14th century. His idea, the guy that did this in the 14th century, his idea was to replace the harmonic series or compare the harmonic series to a series that had even smaller terms, and if the one with smaller terms diverges, then the one with bigger terms must as well. So here's our harmonic series. We're going to replace or compare this to something that has slightly smaller terms. So we're going to replace the half, or the 1 here, with a half. So you'll have a half. Half is smaller than 1, so this is smaller, and then this half will leave a half, and then we'll replace the third with a fourth. So there's a fourth, and a fourth is smaller than a third, so this is smaller, and the 1/4 will leave there. And the next one, 1/5, we're going to replace with an eighth, which is smaller, and the 6th we'll replace with an eighth, and the 7th we'll replace with an eighth, and the 8th we'll leave there, and so on. You're going to do that forever. So the powers of 2 will leave there, and everything between the powers of 2 will bump up to the next power of 2, so that you end up with a smaller fraction, and so you get a smaller series. So this guy is smaller than this one. But now if you just regroup this, we got a half, here's 2/4, which is a half, here's 4/8, which is a half, and so this is a half and a half and a half and a half and a half. And this thing diverges because this limit is not 0. So that was his proof of harmonic series diverging. Now it's kind of curious. If you look at 1 over n squared, you don't diverge, it actually converges, and it's known what it converges to. It converges to pi squared divided by 6, strangely enough. So that might be a little weird that the sum of 1 over n just goes off to infinity, but 1 over n squared converges to pi squared over 6. Though it might not be that surprising if you remember the improper integrals. The integral from 1 to infinity of 1 over x diverges, but the integral from 1 to infinity of 1 over x squared converges. And actually these series are Riemann sums for the integral. So this is a Riemann sum for this integral. and the harmonic series is the Riemann sum for this integral, so I guess it kind of makes some sense. Okay, so how are we going to define the sum of a series? Let's make that a little more precise. So if we have a series, which is the sum of this a sub n sequence, we're going to define a new sequence that's I'm going to call S sub n. S sub n is going to be what we call the nth partial sum of the series, and what we're going to do is add up the first n terms of the series. So the series goes from 1 to infinity. This S sub n goes from 1 to n. So this is a finite sum, and so that's a number. You add up finite many numbers, you get a number. Okay, so S sub n is a number, and it of course changes for each value of n. So this is a sequence, a list of numbers, this S sub n, and this sequence is the sequence of partial sums. Okay, so here's an example of finding the partial sums. I give you this series, find the 10th and 20th partial sums of this series. One way to do this is with Sage's sum command, SUM, and the sum command takes 4 arguments. It's an expression that you want to add up. That's this thing inside here. The index variable, in this case n, where n starts and where the index variable ends. Don't forget to declare the index variable, unless of course you're using x as your index variable, which we don't normally do. Okay, here's the 10th partial sum then. So I declared n to be a variable. What I want to add up is this formula inside here. Don't forget these explicit multiplications in parentheses around the top and parentheses around the bottom. The index variable I'm using is n, and that doesn't matter. It's a dummy variable. I could have made it I or k or whatever you like. I'll just use n here. N starts at 1, and for the 10th partial sum, it stops at 10. So this is just adding up the first 10 numbers in this series. And here's the fraction I convert to a decimal. It's about 1.4. 20th partial sum looks exactly the same, except I go to 20. And that gives me 1.86. Okay, so there's some partial sums. Now that we have these partial sums, we're going to define convergence or divergence of the series in terms of that sequence of partial sums S sub n. Okay, we already talked about last time what it means for a sequence to converge. So if the limit of this sequence exists, then we say that the series converges, or we say the series is convergent. And the sum of the series is defined to be that limit. And if the limit doesn't exist, then we say the series diverges. Okay, so here's a graph of the first 50 partial sums of this series we were looking at above. Notice here that these partial sums look like they're just getting bigger and bigger and bigger and bigger as I go. So, this is n, this is S sub n, and it doesn't look like this is approaching any sort of limit, so I might think this series diverges. Of course, this is not a proof. Maybe if I went out there to n is 500 or 5,000 or 5 million, maybe this would flatten out and approach a limit. Sage actually can do infinite series in many cases. It's the same thing, but instead of stopping at 10 or 20 or 50, just go all the way to infinity. And this case, it tells you get this big error message, which is not really an error at all. It says value error, sum is divergent. So really, this is the right answer. Sum is divergent. So it's not really an error. You haven't done something wrong. So be on the lookout for divergent sums this way. Sometimes it may be that you might get the answer infinity out of here instead of sum is divergent. That might be possible. I'm not sure. I've seen different kind of results come out from different kind of sums. Okay, here is our harmonic series, which I already said diverged, and we looked at a little proof of that from many years ago. Here's the graph of the first 50 partial sums of this series, and again it looks like these partial sums are getting bigger and bigger and bigger without reaching any sort of boundary or limit. And if we ask Sage, it will tell us that this series diverges. So here is the sum of 1 over n as n goes from 1 to infinity, and I get sum is divergent. Okay, here is what happens when you have 1 over n squared. So I told you up above that this adds up to pi squared over 6. which is roughly 1.6. And here's the graph of the first 50 partial sums. And this thing, you can see it's starting to get flat. Right around here at 1.6, it's flattening out. Now again, this is not a proof that this thing converges. But if you compare these graphs, this one, that yes, it's growing slower as you go up here, but it still looks like it's going up, up, up. And this one, which appears to be flattening out. And here's our answer from Sage. It tells the answer is 1/6 of pi squared. That's what I told you the answer was. Common type of series is the geometric series. It's called geometric because the terms of the series, the a sub n, the things you're adding up, form a geometric sequence. Remember, a sequence is geometric if you divide successive terms, you always get the same number. And that's called the common ratio. So if you take the 5th term and divide by the 4th term, it's the same thing as the 101st term divided by the 100th term. You have that common ratio there. So if you have a geometric series, this is kind of the general form of a geometric series. It looks like a, which is the first term, times r, which is the common ratio, raised to the nth power. And here n would start at 0 and go to infinity. So up above, I've been starting all my series at 1, which is really not necessary, which is sort of for convenience sake. It's customary to start geometric series at n equals 0, though it's not required, but I'll give you a formula later that kind of assumes you start at 0. So you start out with the first term a, you multiply by the common ratio, you multiply by the common ratio again, you multiply by the common ratio again. That's what terms of a geometric sequence looks like. Here's an example, 1 over 2 to the nth power. So here, if you plug in n equals 0, you get 2 to the 0 is 1, 1 divided by 1 is 1. So the first term is 1, so the a would be 1. And the common ratio here is a half. If you divide successive terms, you get a half. So the first term is 1. When n is 0, you get 1. And when n is 1, you get a half. And so a half divided by 1 is a half. A half is the common ratio. I want to look at the partial sums of this geometric series. And I'm going to use Sage's sum command. And I'm going to go ahead and separate out the initial 0, the 0th term. So when n is 0, you get 1. I'm going to leave that separate and then see what happens after that. You'll see the pattern easier that way. So right now, this is when n is 1. So we just have n is 0 and n is 1, and you get 1.5. And here's what happens when n is 2. You got 1.75. Here's 3. Okay, 1 plus 7/8, 4, 15 16ths, 5, 31 32nds. And you notice a pattern in this number. So when I separate out the 1, this thing is a power of 2 on the bottom and 1 less on the top. All right, 63 over 64, 127 over 128, 255 over 256, and this pattern continues. And the bigger this number on the bottom gets, subtracting 1 on top makes less and less difference. So there's 10, and the more you go out here, the closer and closer and closer this gets to 2. But here, when n is 100, it's rounded to 2 already. So as n approaches infinity, this guy approaches 2. This series converges, and the answer is 2. The sum is 2. All right, here's the graph of the first 20 terms of this series, and it looks like 2 is where we're approaching. There's actually a formula for the sum of a geometric series. If your common ratio is between -1 and 1, then the sum of the geometric series when you start at n equals 0 is the first term divided by 1 minus r. Well, I guess I should say that it's a over 1 minus r when you start at 0. You can start anywhere you want if you think of it just as first term divided by 1 minus common ratio. So whatever n starts at, if n starts at 10, plug that into the formula. That gives you the first term. That would go on top. And then whatever your common ratio is, you'll just 1 minus that on the bottom. And that's the sum of a geometric series. Okay, so let's look at an example of that. n equals 0 to infinity of 3 over 5 to the n. So what's the first term? Well, you plug in n equals 0. That's where it starts. So you get 3 divided by 5 to the 0. 5 to the 0 is 1, so the answer is 3. So 3. What is the common ratio? The common ratio here is a fifth. Okay, the r is whatever's being raised to the nth power. And what's raised to the nth power here is a fifth. The other way to think about it would be to, you saw the first term, when n equals 0 you get 3, try n equals 1, and you get 3 over 5. So what's 3 over 5 divided by 3? And the answer is 1 over 5. So r is a fifth, a is 3, and so the formula says first term divided by 1 minus common ratio, and that turns out to be 15/4. You could also ask Sage to do that for you. Okay, compare that to example 9. You notice the difference between these two? Here I have an nth power on the 3 as well as the 5. So now the common ratio is 3/5. Both the 3 and the 5 are in the nth power. When I plug in n equals 0, I get 3 to the 0 over 5 to the 0. That's 1 divided by 1. So the a is 1. And so you get 1 over 1 minus 3/5. And Sage gives us the same answer, 5/2. Okay, what about this one? So I told you this is a geometric series, so the pattern continues. The first term is a third. The common ratio is 2/5. How do I know that? Well, take successive terms and divide. So take the 2/15 and divide by the third, and you get 2/5. Or you can take the 4/75 and divide by the 2/15, and you get 2/5, or whatever. Okay, so first term divided by 1 minus common ratio, and you get 5/9. And then, of course, if you want to set this up in Sage, you have to convert this ... to an actual formula. So its geometric series always looks like first term times common ratio raised to the nth power, and n starts at 0 and goes to infinity for that. Okay. I want to explore some various series of this form. So a sub n is going to be the sequence that I'm adding up here in this series. I'm going to let you adjust the starting, where the index starts, so I to infinity, depending on where you want to start. Like 1 over n, for example, that can't start at n equals 0. So anyway, this interact is set up, and I'll put 1 over n in there. And I'll start the index at 1. This says, do you want which partial sum do you want? So you put 10 in there, and it will tell you the partial sum. If you want an infinite sum, you can check this box, and this one diverges. And if you don't want to worry about the infinite sum, you can uncheck that. For some series, it might kind of go slow. So let's take the 100th partial sum. And when you do that with 1 over n, you can see that these just get bigger and bigger and bigger. Here's the 1000th partial sum. And the numbers just keep going up. Now, if you change this to 1 over n squared, 10th partial sum 1.5, 100th partial sum 1.6, 1000th partial sum 1.64, and we'll go ahead and check that. You can see that this one, unlike 1 over n, doesn't seem to get bigger and bigger and bigger. It really slows down. You start adding more and more terms, and you don't increase that fast, and you start approaching some sort of limit. So here's the 1000th partial sum, and here is the actual sum of the series. And let's see, this is different here. So we got 1.64, this is 4, this is 3. So we're not there yet. I don't know how fast this thing will go, how many terms I want to give it. So here's 10,000 terms, and now I got 1.648, and this is 1.6449. So it's still slowly approaching the infinite sum here. Alright, what about this 0.9? 0.9 raised to the n. Now this one, that's geometric, so maybe we'll go ahead and start it at 0 here, and let's take the 10th partial sum. Okay, so this is a geometric series. If you start it at 0, then the first term is 1, and the common ratio is 0.9, 9/10. So you get 1. The sum should be 1 over 1 minus 9/10. 1 minus 9/10 is 1/10, so you get 1 divided by a tenth, which is 10. Okay, good. So our formula agrees. The sum is 10. And here's the 10th partial sum. Here's the 100th partial sum. And I'm getting quite a bit closer to 10. Here's the 1000th partial sum. And to this number of decimal places already rounds up to 10. So this geometric series approaches its sum much quicker than 1 over n squared. Remember, with 1 over n squared, well, I went up to 10,000, and you still only had the first, I don't know, 3 decimal places or something. Here, with at 100, we were already 9.99997. This is already going to round up to 10. So this kind of approaches its limit much more rapidly. What if we had another 9 there? So the sum of this series is 100. Not sure why exactly Sage here has the, it must be doing this as a decimal instead of as a fraction, so it gets 99.9 repeating instead of just 100, but that's the same. And here's the 100th partial sum, adds up to 63. Here's the 1000th, and this one takes a little longer. Here's 10,000 terms, and you start getting very, very, very close to 100. Now remember, I said that the geometric series diverges once you get to 1. When the common ratio is 1, it diverges. And you can see that the closer you make this thing, this is the r, the closer it gets to 1, the bigger this sum becomes. So here at 0.999, the answer is 1,000. And let's go up here, 1,000 partial sum. This one actually grows not that fast. So there's 10,000 terms, and I got 999.95. Okay. And the bigger we make this guy, the closer it gets to 1, the bigger the sum becomes. I got some round off error here. The answer is 10,000. This is some rounding. Okay, and this is 100,000, and so on. If you actually get up to 1, then the series diverges. And it tells you here it's infinity. And anyway, you can put whatever series you want in here. You can play around with things geometric or otherwise, and you can kind of make a conjecture about what's going to happen. Like, what about 1 over, let's see, what if I put 1.5 in here? Start this at 1. Let's see. I'm not sure what's upset about there. I'm just curious because this one, 1 over n, that one diverges, 1 over n squared converges. So what about something in between? So this is the power 1, this is the power 2. What about the power 1.5? What happens there? And this is 2.4, this is 2.5, and it looks like as long as the power is bigger than 1, it looks like this thing is converging to something. Let's see if infinite sum will work now. It doesn't like something about this. I'm not sure exactly why. I don't know if it's this decimal. It might, if I put 3 halves here, will it change its tune? Not sure. If it's thinking about adding that up, oh, I might regret going up that high. With these integers, it's probably trying to keep exact answers until the very end, and so this might be kind of a mess. Anyway, you can play around with this all you want. Feel free to change the starting index, change the expression here that you're adding up, play around with whatever series you like to.